pull up the presentation and see here. I'm going to, okay, share desktop. Let's see what that does. Can you see?
Perfect. Perfect.
Okay.
Looks great. Okay, you have the floor.
Great. Okay, let me do presenter view. Actually, I'm going to try this differently. PowerPoint. Okay. Play from start. Okay, there. Nicole, if
We are seeing something that says give subtitles a try.
Give subtitles a try. Oh, okay, wait a second. Resume share. Is that let me try this again.
Okay.
Zoom. Start share screen. Okay. Share. Okay, now what do you see?
I see your slideshow. Perfect.
Okay, great. Okay, now I'm going to try to go into presenter into full screen mode. Do you still see something?
I see your slideshow. It looks great.
Okay, great. So Nicole, I'll be speaking, and since I don't actually see anybody, if you could at least every few minutes just say looks good or something, so I know that I haven't lost the link and I'm speaking to the vacuum.
I will definitely keep you posted every few minutes.
All right. All right. Well, first, welcome everybody to the Mars Society Summer School. And as you may have been told, my interest is life on Mars. So what I'd like to do is give you an overview of the topic life on Mars, what that means to me. And then at the end, I'll do a little bit of a tangent and talk about life on other worlds too. In a way, it's part of the story of life on Mars is what other worlds are in the mix when it comes to life. So I like to think of the question of life on Mars in three tenses: life past, life present, and life future. And life past is the question, did Mars have life? And if it did have life, was it a second Genesis? And I'll explain what I mean by that. It's a very important point that's not, I think, widely appreciated. The question of life on Mars and whether it's a second Genesis. Then, of course, life present. Can Mars support life? Is it a place where humans can live and work? And I phrase that, as I phrase all of these, as questions. We don't really know the answer to any of these questions. Three questions. Did Mars have life? Can it support life? Those are both questions. We would like to know the answers. And I'll talk a little bit about how we find out the answers. Then there's the final question, life future. Can Mars have a biological future as a planet? And again, this is a question. Sometimes you hear reports as if people think they know the answer already, and it's, of course it's yes, or of course it's no, but we really don't know the answer. Okay, so let's jump in. Past slide, second Genesis. What do I mean by a second Genesis? Why am I focusing on a second Genesis? Well, here in the lower left, you see life on Earth. That's life as we know it. It's a diagram called the Tree of Life that defines life on Earth. And it shows that all life on Earth shares a common ancestor and a common biochemistry. We've only got one example of life here, life 1.0. If we found life on another planet and it was different from ours and had a distinct evidence of an independent origin, in other words, a second Genesis, that would be very interesting. It'd be interesting in two ways. One, we'd now have another example of life, life 2.0, and we could compare the two and learn a lot. And also, if we could determine that in our own little solar system, life started twice, then that would be clear evidence that life is common in the universe. And I've added my editorial point of view on that. Yay. And that's by what you might call the 0-1 infinity rule. There could be zero life in the universe. There could be one, but there's not going to be two. If there's more than one, there are billions and billions, so to speak. And this is a very interesting point, the 0-1 infinity rule. If you're interested in it, Google it. It's got an interesting history in literature and in computer science. And if you're interested in this concept of life on Earth, just Google the tree of life. So what we're looking for on Mars is not just life, but aliens. And we have an operational definition. Aliens are organisms that do not map on our tree of life. They're not related to us. On Earth, so far, we have not found any organism that does not map on our tree of life. It's a little hard to put viruses on the map, but they're clearly part of the same system. They use the same DNA, RNA types. Okay, where to look for life? Mars, our focus today, but there's also Europa, Enceladus, and Titan. These are interesting targets. I've put an icon next to each of them. Mars, two little stars. There's two places where we might find evidence of past life on Mars. Ground ice in the polar regions and ancient dry lake beds in the equatorial region. Europa, very interesting moon of Jupiter, but I give it a black X because the water there is trapped under an extremely thick layer of ice, and there doesn't look like much chance of getting to it anytime soon. Enceladus, similar to Europa, has ocean under ice, but it has the welcome feature of a jet of ice coming out the South Pole, so we can get samples by just flying through. So Enceladus gets a gold star. Frankly, I think it's the most likely place to find evidence of life soon. Titan gets a question mark and an exclamation point. It's a moon of Saturn. It has a liquid on its surface. It has oceans. It has clouds. But those clouds and oceans and rivers are not made of water. They're made out of liquid methane. Hence the question mark. Could there be life in liquid methane? And hence the exclamation point. If we find life on Titan, it is definitely not related to us. We're water-based. Liquid methane-based life would definitely be a second genesis. That would be very, very cool. The most interesting result from a search for life point of view would be to find life on Titan. Okay, back to Mars. Why is Mars such an important focus? Well, first, evidence of past liquid water. You've certainly seen these, going back to imaginary drawings of Percival Lowell, but modern evidence from photographs from orbit and data from the surface, Mars had water, lots of water on the surface, liquid. That's the most important thing we know about Mars. It used to have lots of water. We also know that it has an atmosphere with carbon, oxygen, and nitrogen in the atmosphere, CO2 and nitrogen. And it's been cold for a long time. So if there was life on Mars, it's been in the freezer. So it might be well preserved. Okay, let's talk about why we know there's water on Mars. It's very simple, back to really Viking. Evidence of pictures showing frost on the surface. Evidence from orbit showing channels cut by water, past liquid water. Okay, what's the big picture? For Mars, the big picture is here. It's really a small picture. Mars is smaller than the Earth. Here is Earth today. This is the famous Apollo blue Earth, blue marble picture. And Mars, an artist's conception by the famous space artist Michael Carroll, showing what Mars might have looked like 3.5 billion years ago. And obviously, the point of this is the similarity. Mars was a blue marble at one point, but it didn't stay. Earth stayed, Mars didn't. And the reason is really captured in this picture. This is because Mars is too small. It is 10 times less massive than the Earth, approximately. And size matters. It matters in planets and elsewhere too. Size matters. Because Mars is so small, it does not have plate tectonics. There's no recycling of sediments. It has less gravity. Stuff escapes to space. And it has no magnetic field. So the solar wind erodes the atmosphere. All of those factors cause it to lose its atmosphere and become cold and dry. Why is Mars cold and Earth not? It is not because Mars is further from the sun. If Earth was where Mars is, it would still be a habitable planet. It is because Mars is smaller than the Earth. If Mars was where Earth is, it would still be cold and dry. Size matters here more than location because both Earth and Mars are in the habitable zone of our star. but Mars is not habitable size for long-term habitability. It's okay for short-term habitability. It may have been habitable for a few 100 million years, but Earth has been habitable for 4.5 billion years, 4,500 million years. Okay, one point I want to make in this artist's conception of Mars is the artist didn't put any ice in. Where's the ice? Even when Mars was wet billions of years ago and warmer than today, it was still cold and had ice. Earth has ice. You can see Antarctica in this Apollo picture. Mars should have had ice, not just at the polar caps, but extending pretty far down, even during its warm period. I'll come back to that later. Okay, I want to talk a little bit about the Phoenix mission to the polar regions in 2008. This was a lander. Landed at 69 degrees north, 60 something, I think it's 69 degrees north, dug down to find ice. It landed. The exhaust from the engines as it landed blew away the dust and revealed ice on the ground right below it. Patterned ground all around. Digging down, we found ice in ice cemented ground and massive ground ice, looked like buried snow underground. We found carbonates, soil pH of 8, very unsurprising, ice, everything worked fine. The big surprise was perchlorate, 0.5% perchlorate in the soil. Chlorine is in the form of perchlorate. Those of you who do model rockets may know that perchlorate is used in rockets, solid rockets. It's a very strong oxidant when it's heated up. Why is it present on the soil of Mars? We don't really know, but it's puzzling. University Valley, Antarctica is a place on Earth that's the most like the Phoenix landing site. There's there's frozen ground with ice underneath the surface, cold, very dry. It's Mars on Earth. It's Phoenix, the Phoenix analog to the Phoenix site. There's life in this soil, but not much. It's very hard to detect, even with our most sensitive DNA extraction methods. We are still struggling to detect the evidence of life, but we know it's there. We can find and culture occasional organisms out. So we know there's life there. We just don't understand how it's working, and its concentrations is so low that our current methods for searching for life don't work. And I take that as an important lesson. If we can't understand life here in Antarctica in the dry valleys, we're not going to be able to do a very good job on Mars, which is even colder and drier. Okay, next mission I want to talk about is the one that's on Mars now, Perseverance. Landed February 2021. It's the second big rover on Mars. It landed here in the X in Jezero Crater. So this is Jezero Crater, 50 kilometers across. This is what the artist's conception of Jezero Crater 3.5 billion years ago, full of water. So if Perseverance had gotten there 3.5 billion years ago, it would have had a splashdown. But we were late, 3.5 billion years late. And so we got there, the water was gone, it's dry. But again, this artist picture is wrong. There should be ice. So I have to Photoshop the ice in. This is what that crater would have looked like 3.5 billion years. Not this. It looked like this. This looks like, Miami Beach or something. This is what it looks like. The Arctic Ocean, ice-covered lake. But ice-covered lakes are fine for life. I'll get to that later. Here is what we see at Jezero Crater. We see sediments, rocks, ground, very much like what we see in the Atacama Desert of Chile, another Mars-like location, and the Antarctic dry valleys. Away from the lakes, we see these ground, very cold, very dry, very lifeless. But we also can study ice-covered lakes in the Antarctic. There's two sets of them, Lake Untersee up in the upper part of this picture and the McMurdo dry valleys in the lower part. These ice-covered lakes on Earth in the Antarctic are our best models for the Jezero Crater. Here is Jezero Crater on Earth. Remember, University Valley was the Phoenix site on Earth. This is the Jezero Crater site on Earth. This is a lake. It's called Lake Untersee, which is redundant because Untersee means lower lake in German. So this is Lake Lower Lake. It was discovered by the Nazis, actually, when they were mapping out this part of Antarctica as trying to find a place to build a submarine base. Anyway, the history aside, this is a ice-covered lake. This picture is our camp on the surface of the lake. We are on the lake, and we are there in the warmest time of the year, December, end of December, early January. This is the South Hemisphere. The lake is ice-covered all year round. The surface around the lake, the ground around the lake, is cold and dry and lifeless. Well, we've been studying this lake, drilling holes in it. Those of you that live in places that get cold would recognize the Jiffy drill here, but we've added many more flights than you probably have ever used. We take water samples that way. People have done that before at this lake, but we did something that no one else had ever done before, which was cut a big hole in the lake, hole big enough to dive through. So this is me getting ready to dive, my first dive in the lake, tethered to a rope for safety. This is kind of like cave diving. You have to go out the way you went in. You can't just pop up, free ascent to the surface and look around and then decide which way to swim. And we are using dry suits, of course, and full face masks for communication. What we found, and we only found it because we went into the lake in person. People had, and we did, sampled the lake with these remote tools, and they hadn't discovered this. And at the bottom of this lake are mounds built by microorganisms, mounds 30 centimeters high, built by microorganisms. And these mounds are thousands of years old, built slowly over time. They're intact because there's nothing in the lake besides microorganisms. There's no tadpoles, there's no fish, there's no minnows, there's no frogs, nothing that would eat the algae that are growing and the cyanobacteria and the diatoms that are growing on these mounds, nothing to disturb them. It's kind of funny, we human beings were the first vertebrates in this lake ever. There are no vertebrates in this lake, only microorganisms. And now microorganisms and visited by a few people who quickly leave. Well, let's go back to Mars, Jezero crater. One of the most interesting pictures we've seen from the rover there is this mound, which clearly looks like sediments, likely to have been deposited when this was a lake. So if the bottom of Jezero crater had these kind of things on it, their remains are trapped in these sediments. That's what we hope to find. And the rover is trundling around looking for these things. So far, it's found evidence of water, but no good evidence of organics. So we're still searching, The rover mission is not complete. It's still going well. Okay, that's the status of the search for life on Mars. 2 sites, 2 stars, remember? Polar sites, life in permafrost, life in cold places, and that could be modern life, and then ancient life in the craters in these sediments at Jezero crater, based on analogy to the lake in Antarctica. You notice that for both of these sites, I'm pointing to a place on Earth that I think is the model for how life might have survived and how its remains might be found. This is a very important approach, in my opinion. Rather than just making things up, we go to places on Earth that we think are the most likely analogs, and we investigate them, and we use that as a basis for our understanding and for our search. Titan, now let's move to the outer solar system. Titan and Enceladus. Enceladus is a very small moon of Saturn. It orbits in the E-ring. You can see it here. Very interesting because in 2005, Cassini discovered, or rather I should say Cassini confirmed, the suspicion that this moon had a geyser on it. There was evidence, mainly the E-ring, that Enceladus was active, water was jetting out. Cassini confirmed this. These are the images showing the geyser, and this on the left, on the right, is a contour of densities. The left is the actual image of water jetting out from this little water ice moon. And by flying through the plume and characterizing the chemistry, Cassini basically put the picture together. There's 10 to 20 kilometer layer of ice. There's a 60-kilometer slightly salty ocean. And then there's hydrothermal vents underneath it. This is amazing. This is the most Earth-like, ocean-like environment we've seen. All the resources requirements, all the requirements for life are there. This is the measurements going of the plume. This is not just water coming out of this lake. It's water with organic material, with ammonia, with hydrogen, with all the resources needed to support certain types of life, especially, for example, microbial, anaerobic microbial life. A particular organism that is the model here for Enceladus would be methanogens, that consuming CO2 plus hydrogen and producing methane. They would love to live here. They have everything they need. This could be a place with life. And the ocean water is coming out into space. We don't have to drill. We don't have to dig. We don't even have to land, really. We could just fly through and grab samples, free samples, take one. So that, I think, is a really exciting near-term opportunity. And there's currently missions being designed that would do just that. Fly through the plume, take samples, and analyze them there. Ultimately, I'd like to fly through the plume, take samples, and bring them back to Earth, but that's harder. Okay, the last mission I want to talk about is to Titan, called Dragonfly. This is an approved mission. It is being built. It's funded. It will launch in 2027. So that is just 4 years from now. And it will land on Titan in December 2034. Mark your calendars, December 2034. It will fly in and start flying from the entry and then find a place to land. And it will do two things that are it'll do a lot of science to understand Titan, a very interesting world. But it'll do two things that are directly relevant to the search for alien life on Titan. First, it will search for variations in hydrogen. And why that? Well, our calculations and chemical theory indicate that if there's life on Titan, it is eating hydrogen. So if there's something eating hydrogen, that might be a signature of life. The Dragonfly will also have a mass spectrometer to detect the molecules of life, to see if there's a certain selectivity that life leaves in the molecules it selects. So here is a video of the entry. Titan, this is going to be an amazing mission as it flies in on the parachute, just like all other missions. But unlike any other mission, it deploys not from landing, but from entry. So it just drops out of the parachute and flies to the ground. So the first thing it does is fly to the ground, find a safe place to land and land. And then it radios Earth and says, hey, the Dragonfly has landed. All automatically. Titan is at 10 AU. It's 80 light minutes away on average from Earth. It's not a remotely controlled. This is autonomous landing. After it's landed, it takes off, does science, takes off, goes land somewhere else, continues that. And it does that over and over again. And it can do that repeatedly because it's a nuclear powered spacecraft. It could, let me see if I can run the video again. It could continue for, a decade easily. Okay, well, we'll skip running the video again. I now want to ask a science question. If we find stuff, organic material on Mars, either in the Phoenix site or in the Perseverance site, the ancient sediments, or if we do get through the ice on Europa, or if we collect it on Enceladus, or on the Dragonfly mission, how can we tell if that organic material was ever alive? The search is not a search for organic material, it's a search for life. So if we find organic material, we have to be able to tell, is this life? Is it alive? Is it dead? Dead is the same as alive. Don't take this too seriously, but dead is the same as alive, and that is an indication of life. Non-life is not dead. It's not alive. It's not dead. The organics in a meteorite are non-life. They're not dead. If you find a dead rabbit in your front yard, it's dead, but it's evidence of life. If you ponder that a little bit, you'll understand what I mean. Life, in fact, the most common state of living matter is dead. Right? And it's most likely what we're going to find on Mars, certainly, Europa, even Enceladus or Titan, is dead remains of organisms. If you dig into the soil on Earth, most of the organic material you find in the soil is the remains of previous dead organisms. Okay, so if the life is like us, it's easy to tell it's alive. We just look for DNA, for example. But what if it's alien? Then it may not have DNA. Then how do we tell that it was alive? Let me first focus on this question of life versus non-life. So here are 3 pictures of organic material. A meteorite, Tagish Lake meteorite. A jar from my laboratory at NASA, Ames, in which we made Titan organics, and picture of a flower. One of these is, all of these are organic material. Only one of them is alive, the flower, obviously. The other 2 are organic materials that are not alive. One, the Titan tholin, is organic material that's made in the laboratory out of simple chemicals, methane and nitrogen, in particular, occasionally water. You can make organic materials. That's basically the famous Miller-Urey synthesis experiment. Put a bunch of gases, put a spark, and organic materials get made, including amino acids. And organic materials are found in meteorites. Also, we don't think that has anything to do with life. They're just in space. There's lots of organics in space, and nothing to do with life. Well, how do we tell the difference? If we find organic material on Mars, how do we know whether it's from a flower, from a lab experiment, or from a meteorite? Well, the answer, we think, is in the pattern of the organics. In all 3 of those samples, we could find amino acids. Amino acids are the basic building block of protein. If you're not familiar with amino acids and their role in life, Google it. Go to Wikipedia and read about amino acids. A very important part of space exploration is understanding amino acids. Amino acids come in 2-handedness, just like your hands. Right-handed called D and left-handed called L, dextrose and lactose. They are symmetrical. They are mirror images of each other. In chemical and in meteorites and in chemical synthesis experiments, amino acids are found more or less the same concentrations of left and right. But if you look at the proteins in living things, like a leaf or a bacteria or a human being, all the proteins have only left-handed amino acids. Proteins are a link, a chain of left-handed amino acids. Life uses some right-handed amino acids, but not in proteins and not very much. So that pattern could tell the difference. If you analyze the organic materials in these 3 samples, one of them would have a lot more left-handed than right-handed in all the amino acids. The other 2 would be a mix. That would be the signature that one of them could be biological. So I represent that graphically here. Biological systems have a distinct pattern. They don't just use random molecules, they have a distinct pattern. And an alien biology, like on Titan, might have a distinct pattern, but with different molecules. So the pattern, the idea of a pattern might be the same, but the particular molecules might depend on whether it's Earth life or a different life. So that's our current strategy, not just for searching for life as we know it, but for searching for life as we don't know it. Look for patterns in the organics, and Dragonfly will be able to do that. Okay, I want to end with some contemplation. I gave a talk, basically this similar talk to this, to public audience in Death Valley when we were down there doing some field work, and a 5th grader asked me, what will you do if you find a second Genesis on Mars? What will you do if you find life on Mars and it's a second Genesis? And I said, that's a very good question. And the answer is, we don't know. We don't discuss that. There's a lot of discussion on missions to go find life and how to find it, and virtually no discussions of what do we do if we succeed? And I said, we are like the dog chasing a car. We are unprepared for success. What's the dog going to do if he actually catches the car, right? It doesn't have a clue. Well, we haven't really thought through what are we going to do if we do find life on Mars? And it is a second Genesis. What does that mean? What do we do about it? And I think that's a question that we do need to consider. And we should consider it before we find it so that we're prepared. And my thoughts on it is that it will matter a lot if we find life, and it will matter even more if that life is a second Genesis. If we go to Mars and find life there, and it represents the first evidence of life in the universe that is not life as we know it, that is historic, both from a humanities point of view and from a science point of view, right? And I think that's going to have moral and ethical implications. Right? On Earth, we really don't give much moral consideration to microorganisms. We give a lot of moral consideration to cats and dogs and horses and bears and polar bears, big cuddly mammals, smiley faces, but not to microorganisms. But maybe we would if we found a microorganism on Mars that was the first example of life, not as we know it. The first time we could say it's life, Jim, but not as we know it. And so what would we do? What does that mean? If we take the view that that is important, what does it do? I think my conclusion is that it means that we should be able to reverse any contamination we put on Mars. So to say it's in a complete sentence, robotic and human exploration of Mars should be done in a way that could be biologically reversible. We must be able to undo, Control Z in the computer parlance, our contamination on Mars if we discover a second genesis of life. Now, one might take a more extreme view and say, well, we should just not go to Mars. We should explore it only remotely. We should not even contaminate it. Then we don't have to reverse the contamination. But it's too late to close that barn door. We have already contaminated Mars. That is not an option. And it also doesn't make much sense because decontamination is not that hard. Doing exploration of Mars without contaminating it is very hard. So, including human exploration. This picture, human base on Mars, can be decontaminated if we decide we needed to. And the reason it can is because the surface of Mars is not a place where anything released will grow. On Earth, we think of biological contamination as irreversible. We take 2 rabbits to Australia and then you never get rid of them, right? Now that's because rabbits can grow in Australia. If you took 2 rabbits to Mars and threw them out on the ground and then decided you wanted to get rid of them, you just have to go find their 2 dead bodies not far from where you put them. Nothing grows on Mars. So decontamination is not irreversible as it is on Earth. Biological decontamination is not irreversible. So Mars helps us, but that's a practical way to approach the question. And now, just briefly, I want to turn to the final part, which is the future. Does Mars have a future? Could we imagine bringing back the water and making it habitable once again? And then on that, I think that's the big question. And to my mind, that is the ultimate question. Why are we going to Mars? Well, to search its past and understand its past. But even if it doesn't have a past, a biological past, even if there was never life on Mars, the real question about Mars will then be the future. Can it have life in the future? And can we humans be the agents of that change? Okay, I tried to keep short on time so that we would have time for questions. So I'm going to stop sharing and let's see, stop sharing and get back to regular Zoom.
Thank you. Wonderful presentation, Dr. McKay. We have several questions. I'm going to try to put them in an order that's kind of makes sense.
Okay.
You've talked a lot about water and organics, and the students heard about that yesterday as well in the lectures. Can you give a very brief description of why water and why organics is so important to the search for life?
Yeah, that's a good question. And it ties what I think all that we know about life and the search for life All that we know really is that on Earth, life is made of organics and lives in water. That's a one sentence description of life on Earth, made of organics and lives in water. So when we're looking for life as we know it, we're looking for organics and water, because life on Earth is made of organics and lives in water. But we have to be careful. On Titan, there is no water. So what are we looking for on Titan? We're looking for made of organics, but lives in liquid methane. And some people might say, well, what about life that's not made of organics? And yeah, if we see environments that may be suitable for that kind of life, we should be on the lookout for that too. But on Earth, the one thing we know is life on Earth is made of organics and lives in water. So that's the first thing we do. And I think the logic to that is, let's look for what we know about first, but keep our eyes open and keep our intellectual thoughts alive to the possibility that life in the universe may be more varied than the one example we have on Earth. We have to be modest about what we can conclude based on only one example.
Great, thank you. Why is finding life on Mars, why would that be important to a human mission to Mars?
Well, I think finding life on Mars, searching for life on Mars, is important for a human mission in a variety of ways. First, and most immediately, if there's life on Mars, it could pose a hazard to humans. You can watch any B-rated science fiction movie and you'll realize that life could be a hazard. The medical office at the astronaut office, the medical officer at the astronaut office will want to know if there is life at the site that the humans go to. That's astronaut health and safety and return to Earth. If those astronauts are to come back to Earth, we, citizens of Earth, will want to know whether or not they're bringing back with them any life from Mars. So those are purely practical issues of health and safety and return to Earth. There's also the scientific issue. If there is life on Mars, it could represent a scientific bonanza. Everything we know about medicine and agriculture is based on studying one example of life. If suddenly we now have two examples, that could really open up huge insights into the nature of biology and have practical implications in medicine. And finally, there's kind of an ethical point of view. If we find that there's a second Genesis on Mars and there's life there, and it's still there at some level, then my recommendation is that we encourage it. We alter Mars to enhance the diversity and scope of that life. Now, there's a difference of opinion here. Some people say, well, no, if there's life on Mars, we can just put it in a jar and put it in the laboratory and then, clear the ground and move in. And some people say, well, just ignore it, just move in and trample it. So you have this, and another point of view is we should just leave it alone. If there's life on Mars, we should quarantine the planet. We don't go there. We don't let it come here. We just leave it alone. I think that's a mistake. It's like if you find an organism, if you found a dog on the side of the road not doing well, you're not going to just ignore it. You're going to try to take care of it. Mars, if there's life on Mars, it's not doing well. So we have an obligation, in my view, to help it. Let me summarize. The views on life on Mars are study it, but put it in a jar and put it in the lab. Quarantine it. Don't stop exploring. Don't go to Mars anymore. And finally, help it, expand it. And I take that latter point of view. Astronauts will play a key role, and human exploration will play a key role in searching for life on Mars. I actually think that until we have human exploration programs going, we're not going to know the answer to the question, is there life on Mars, with any certainty, because the infrastructure and the capabilities that human exploration brings, for example, deep drilling, being able to drill down 1 kilometer, 2 kilometers, are necessary to do the search. So it's part of the story.
Thank you. Great answer. And a question from Joan. How do we know the kinds of materials? Oh no, where'd the question go? How do we know the kinds of materials on planets we have never been to?
Well, that's a good question. Let's take the case of Mars. One of the first and most interesting experiments on Mars, on Viking, was what's called an X-ray fluorescence instrument. This is a little box that shines X-rays and then looks at the light that emits from those X-rays, called X-ray fluorescence. And you can actually get one that's like the size of a small, phone or something, and use it on Earth. We use it in the field. You can put it on a rock, pull the trigger, it will shine X-rays into the rock and read out the light that comes back and tell you what elements are in that rock. Geologists use it on Earth. We put one on Mars, so we know the elements that are there. And we have other instruments that do similar things, but that instrument is particularly interesting because it's so versatile and it's commonly used here on Earth. If you go into geology and study rocks, you will probably get one, a handheld, looks like a little gun, like a little drill, handheld X-ray fluorescence, and you can point it to a rock and it'll tell you what the rock is made of. There's other instruments like Raman spectroscopy that can do similar things for different applications. So that's how.
Spectroscopy really has changed our understanding of everything on Earth and in the universe.
Right.
Okay, from James, do you think there are some places on Mars that have a greater chance of supporting or finding life? If so, what places?
Yes, I think the places on Mars that have the greatest chance of supporting life are the polar regions where there's ice. The greatest chance of finding evidence of life could be also in the old cratered lakes in the equatorial region, but their life is probably not alive, but they would still have organic evidence of life.
Okay, and from Medi, if there were life on Mars, wouldn't satellite images show us?
No. If there was life on Mars, it would be microscopic. If there was trees and forests on Mars, yes, we would see it in satellite images. But if there's microscopic life, no. Imagine flying over the satellite over the Atacama Desert. No evidence of life there. But if you get down on the ground and dig into the soil, you find evidence of life.
And from Hanan, how long as a human can we stay on Mars?
That is a very good question, and we do not know the answer. Even if you provide life support, and even if you provide everything humans need to live, you cannot provide higher gravity. Mars gravity is 1/3 the gravity of Earth. We don't know what the long-term effects will be. Some people, we sort of assume that it won't matter, that 1/3 gravity will be fine. But we don't know that. We won't know that till we try. So the first humans on Mars will be guinea pigs. We'll see how it goes. And it could be that there's no effect, no detrimental effect on adults, already grown adults, that you get used to the third gravity. But it could be that there are detrimental effects on pregnancy, also on newborns as they develop, or it could be not. We don't know. That's one of the deep questions that we have to answer before we know if Mars can be a place where humans can live and work.
Good answer. From Tissia, if everything on Mars is biologically reversible, how are we planning to flourish on it?
Well, if we were to go to Mars, we could build a base. We could have greenhouses in that base, inside growing plants, even have small animals. We could support ourselves on that and have it all contained in the base. There would be inevitable leakage out of the greenhouse and out of the base. Most of it would be destroyed by the solar UV on Mars. If at some point we decided to reverse the effect of that base, we would just take apart the greenhouse, collect all the organic material, and clean it up the way we clean up Superfund sites on Earth, actually. We know how to decontaminate sites. We do it on Earth after, for example, nuclear spills or chemical spills. We would do the same thing. So it's not intrinsically in conflict. Biologically reversible exploration does not prohibit human exploration. It just means we have to be careful when we clean up, if we decide to clean up, if we find the evidence of a second genesis.
And another question, what do you think, 0 to 100% chance, what do you think the percent chance of us finding extant life living on Mars now?
Well, that's a hard question for me because obviously I'm spending a lot of time searching for it, right? I spend all my time planning missions to search for life on Mars. So I better have a pretty optimistic view that it's there, right? So I'm not an unbiased observer. So I think the chances are good enough to warrant $1 billion mission, right? So that's probably the best I can say. But I also admit that if there is no life, the mission must be designed in such a way that its results are interesting, even if there's no life. It must tell us other things about Mars too.
Okay, there was another question, but it disappeared. Okay, any other questions from the audience while we have the wonderful Dr. McKay here with us? I appreciate you helping us again, and life on Mars is my favorite subject.
Me too. Yeah. Another unbiased observer.
And let's see. Okay, well, thank you very much, Dr. McKay. Students, if you'll hang on just another minute after Dr. McKay logs off, and we will keep you posted on the results of our contest. Thank you very much.
Okay.
Bye.
Goodbye, everybody.
Okay, so for those of you who may have joined late, if you saw the spreadsheet I shared with everyone to put your name and time zone, that would help me get all of the teams ready. So you should all have access. If you don't have access, send me an email and let's get your name and your time zone so I can put the groups together. If you don't feel comfortable sharing your email address publicly on this with the entire group, it doesn't go out to like the general public, but just to the group, just email me separately. Even if you emailed me yesterday, fill that in because I got a lot of emails and I don't want to miss anybody. Does anybody have any questions right now? Our next talk is at 1:30 Pacific time, and I believe that's Ashwini Ramesh, and I will see you all in a couple of hours if you don't have any questions. Okay, thank you. Okay, Mehdi, we will have this recorded, and the next one will be recorded, and they will be uploaded. The webmaster is working on the ones from yesterday. So give about 24 to 48 hours for those to be uploaded, but you will receive them. They will all be linked on the syllabus. So if you can't come to the live, because I know everyone's spread around the world, if you can't come to the live session, the recordings will, in good time, within the next day or so, all start to be linked into the syllabus. And if you want the ones from yesterday, if you didn't get it, just email me. Okay. Anything else? I hope I'm saying your names right too. If I'm not, just send me a little note on the chat and tell me how to pronounce it. Okay, everyone. I'll see you in a little bit. Thank you. Bye.